Hello, welcome to this tutorial video for Globular, the proof assistant for high category theory. In this video we're going to see the basic features of the interface and construct a proof of the fact that every equivalence in a 2 category gives rise to an adjoint equivalence. We're going to do this in two ways, first by creating all the cells by hand, and second by using Globular's automatic invertibility handling. Okay, so to start we've loaded the webpage globular.science. We're using the Chrome browser, which is where Globular works best at the moment. To start off with, we just have a single zero cell, a single object for our high category. To define an equivalence, we're going to want a second zero cell, so let's click new zero cell. Let's give them more friendly names. I think I want to call them A and B. We could also change their colours by clicking on this colour bar, but I quite like the default colours. We now want some one cells. We want a one cell going from A to B and its inverse going from B to A. So to define a cell going from A to B, first we click the cell we want to be its source. That's A. It comes up big here, we can hover over it to see what it is. We click source. A little preview appears in the bottom right to remember what we've decided to use as the source for our new cell. We now click B, which we want to be the target, then we click target and our new one cell appears. Let's call it F. We now want to define its inverse. The source of the inverse will be B, so let's click B. Instead of clicking source over here, I'm going to press S on the keyboard. That's the shortcut. The target will be A, so I click A, and I press T. And now we've got F inverse. We now need some two cells to say that F and F inverse are in fact inverse to each other. So the first of those will be from the composite of F with its inverse to the identity. So let's build that composite. We start by clicking F, and a diagram of F appears. We then click F inverse, which we want to attach to it. The possible attachment zones are highlighted. We see we can attach it on the left or on the right. Let's attach it on the right. We've now got our first composite diagram. We can move our mouse over it to see what's going on. We start with A. We then have F, which takes us to B. We then have F inverse, which takes us back to A again. These labels, of course, are coming from these names we've assigned here. We want this to be the source of a new 2 cell. Let's press S. And the target we want to be the identity on A. So we click A, press I for identity, and T for target. And now we've got our 2 cell. Let's call that red cap. In a similar way, we can build the other 3 2 cells that we'll need. Click A, press identity, source, form the composite, press T, click B, identity source, form the composite target, and similarly for the final 2 cell. So now we've got all our 2 cells. Let's give them more friendly names. Red cup, blue cup, blue cap. Now we want to input the equations that say that red cap and red cup are inverse to each other, and blue cap are inverse to each other. The way that equations are input in Globular are again just as higher cells. Everything in Globular is a higher cell. So the first equation we want is that red cap composed with red cup can rewrite to the identity. So we perform the composite, we press S, we take the identity of A, press T. Here's our 3 cell. We interpret this as saying red cap, red cup can turn into the identity. We also need the reverse. Okay, now let's continue to do this for the rest of our structure. Whoops, that's a mistake. So here I've attached more than I want. I can click and drag off the top and it will cancel. Press T, okay. So now we've got 4 of our 3 cells, but this only says that we have invertibility on one side. We also need invertibility on the other side. So I can propose, I click S, the target here will be this composite, and I take the identity, and press T, that's the target. Okay, so let me quickly finish building these composites. As you can see, building composites in Globular can be relatively quick, as long as you know what you want to do in advance, and use the keyboard shortcuts. Great, okay, so here are all of our 3 cells. Now, let's start building our proof. So we want to prove that we can redefine one of these 2 cells to get a new 2-cell which satisfies the snake equations with the rest of the structure. So let's see how that works. We're going to redefine this red cup. So let's build a diagram that we're going to use to be its redefinition. We'll start with this. Now we'll attach the blue cup. So we click here and we click its attachment point. Now we want to attach the red cap. So we click here and we click its attachment point. So we've built this hockey stick shaped diagram. This is going to be our redefined red cup. Now we click H for theorem to store what we've done. That does two things. Firstly, it creates a new 2-cell whose source is the source of the diagram we were just looking at, and whose target is the target of the diagram we were just looking at. That's this thing, it's called cell 17. I'll call it new red cup. It also creates a cell of dimension 1 higher, in this case a 3-cell, which tells us what that new cell means in terms of our previous structure. So it's created this cell 18. We'll call this new red cup definition. Okay, so now let's start our proof. We want to construct the snake equation, show that it holds. So we click on new red cup. We're going to whisker with a 1-cell on the right, and then we're going to attach a red cap. No, that's the wrong thing. We're going to attach a blue cap, I'm sorry, over here on the right. Okay. Now we're going to build up a proof that this can be rewritten to the identity. So to do this, we start by taking the identity, because we want to build a 3 diagram, not a 2 diagram. The 3 diagram will be our entire proof. So we click I. We've now got a 3 diagram with 2 two-dimensional slices, which are just the same as each other because it's an identity 3 diagram, and we'll start at slice 1, which is the target slice, because we want to compose to the target of the 3 diagram to form our proof. Right, the first thing we're going to do is apply the definition of new red cup. Here it is, we click, we see that Globular has found where we can apply it, the application has taken place. The next thing we want to do is cut through here in a certain sense. So let's find the local model for that in our list of 3 cells. Here it is, we click, we see there are several places we can apply it. Oh no, that's wrong. We want red on the outside and blue in the middle. So that's here, we click this one. We want to cut here. So we click, and we've applied our cell. Now we want to exchange the heights of the blue cup and the blue cap. We see here that they're free to move relative to each other, so we can apply an interchanger. We click and drag, and the interchanger is applied. Now we want to merge these 2 cells together. So where's the local model of that? Here it is. We click, and we apply. Now we need to apply some more interchangers. So click and drag, and we see we've got this diagram here where again we can now cancel some structures. We need to apply this here, and we need to cancel that blue bubble in a sea of red. That's here. Click and cancel, and we finished our proof. We can go back and review what we've done by using the slice commands. Here's our lovely proof. But we can also project out 1 dimension and see our entire proof as a single 2D diagram. This is like a higher Morse projection. We increment the project counter, and here it is. In this projected diagram, the vertices are 3 cells. You see here this is cell 11, which was the last cell we applied. Here it is, it's a 3-cell. The edges are 2 cells, and the regions are 1 cells. In this case, every region is F. Now from this view, we can modify our proof. The proof we performed was actually so efficient, I don't think there's any shorter proof we could construct, but we could make our proof more complicated if we wanted. We could take this cell and we could pull it through underneath that red strand. We could pull this up. Here we've just pulled up, and Globular has noticed there's multiple things that click and drag could mean. It could mean we want to apply an interchanger, or it could mean we want to pull this cell 16 over another strand. So let's say we wanted to apply the interchanger. And now perhaps we can drag this over here. So you can't always drag a cell over another cell, because from the projection you can't see everything you're allowed to do. Globular will only ever let you do something if it makes sense high categorically. Let's try. Can we perform a crossing here? Surely we can do something. What can we do? We could do this. So now here, this is an interesting situation. We've got a crossing, a crossing, a crossing, and if you look, this is a situation where the third Ridermeister move will apply. So we can click and drag, and that third Ridermeister move will be executed. could do this again, we could pull this up. Here we see we've got an interchanger inverse and an interchanger. These crossings can annihilate each other. The way we do that is select one of the crossings and pull down. And we're back to where we started. Let's modify our proof again in a rather foolish way. If we modify our proof, then we can unproject and slice through, and we now see that modified proof. See, it's now 12 steps. It involves some pointless steps where we interchange and uninterchange, which were the steps we inserted here. We can go again and simplify, and we see that we're back to our nice efficient 8-step proof. Okay, so that's an example of how to prove something in Globular through creating cells directly in the interface. That was fine, didn't take us too long, but there's a lot of algorithmic steps that we had to make to expand out what we meant by F being an inverse equivalence. It was quite tiresome having to input all these cells, and it would be nice if Globular could do it automatically, and indeed it can. That's what this invertibility toggle here does. So let's use that. We're going to get rid of all the other structures that we don't want now. So we're going to delete F inverse, click, and we see that all the other structure below disappears. That's because when you delete a cell, all the structure that uses that cell is also deleted. So now let's make F invertible. Now we can jump straight to the step of creating the new cup, because all the other structure just arises from checking this box. So how do we create the new cup in this mode where we're using an invertible cell? First we create F. Now we want to attach F inverse on the right here. F inverse is higher structure that arises co-inductively from the fact that we've clicked this invertible toggle, and all that higher structure in this mode of Globular is applied by clicking or clicking and dragging on a diagram. So first of all we're going to click here to apply the inverse of F, click, and we see we hover over. Globular knows this is F inverse and this is F, even though we never entered F inverse here as the name of any cell. Now we're going to take the identity. Now to form a cup we're going to pinch off at the bottom. So we click F at the bottom and drag to the right, and we pinch it off. Now we want to create a bifurcation here at the top, so we click here, and Globular knows what we want to do, and we click here and drag to the right, and Globular knows what we want to do. So very simply we've created this same hockey stick figure again. Now we click theorem in the same way. Let's again call this new red cup, and let's call this new red cup definition. So now again let's try and prove the snake equation. We click here. Now we want to attach F. We can do that by just clicking on the right hand side of the diagram and it will appear. Now we want to pinch off the top here, so we click and drag. We see we formed our snake. This is the cancellation of F with its inverse, which is generated automatically as structure by ticking this box, but this we see is new red cup. It's the structure that we explicitly defined here. So now we want to start constructing our proof. So we click identity just as before, because we want to build up an entire three-dimensional proof object. We don't just want to modify this two-dimensional structure. And we navigate to the target slice because we want to attach to the target. Now we're going to first we want to expand this definition of new red cup just as before. We want to apply this 3-cell, and conveniently we can do that just by clicking the locus of attachment. So you see the expansion happens immediately. The next step is to cut through here. Before we had to hunt and search down the left hand side, and I think I made a mistake at that point trying to find exactly the cell that we can apply, but now we can just click and drag and cancel. Now we want to apply an interchanger here, so we click and drag. Now we want to cancel F inverse insert with F inverse cancel. Again we click and drag. Oh, now Globular's noticed we can do two different things here. We can interchange, or we can F inverse cancel cancel. Okay, so I've clicked the wrong thing there. I've clicked the interchanger. That's alright. We can just go back again. And so we've introduced a little wobble in our proof, but later on we'll be able to iron that out by the when we do the Morse projection and we see the structure of the entire proof. So now let's annihilate these, cancel, let's interchange, interchange, annihilate, cancel, annihilate. Okay, and we've finished. Let's project. We see a very similar diagram to what we constructed before, except we made a mistake, albeit a deliberate mistake. We have an interchanger, interchanger inverse. So we can cancel those out and we get our nice efficient proof. We can click theorem at this stage if we like, and now we can call this snake theorem. Here it is. It's a single 3-cell that lets us rewrite this snake to the identity in one step. And then here's the proof. We call it snake proof. Okay, so that's the end of the demo.